And welcome back, everyone. This final piece associated with Chapter 6 takes us to the conclusion of our work with spherical harmonics, and we continue to explore angular momentum, and it's the spherical harmonics that actually carry the angular momentum piece for the atom. And so this is a nice transition into Chapter 7 where we start to look at the atom. So keep going and enjoy, leave your comments below, and I can address those questions in a future video. All right, speak to you soon. That L was equal to 1. Okay, so 2 times 1 plus 1, which is equal to 3. So there are 3 values of m. Okay, and we know, of course, that those values are going to be 0 and then plus and minus 1. Okay, so those are the values of m that we care about. Now let's take this a little bit further. I'm going to write out the expression now for m is equal to 1. We're gonna think about angular momentum for this specific case where L is equal to 1. So let's just rewrite this equation here. L squared y L m theta phi equals, now we're going to plug in these numbers because now L is equal to 1, so we've got a 1 in here multiplied by 1 plus 1 times h bar squared, and this is our eigenvalue equation. Okay, and that ends up being equal to 2h bar squared y L m theta comma phi, and of course we already know that m is equal to 0 comma plus or minus 1. Of course, we also recognize, this may seem a little tedious, but we also know that L sub z commutes with L hat squared. So we know that's equal to m h bar y L m theta comma phi. Okay, so again we've got m being equal to 0 and plus or minus 1. So actually we know that there are 3 values for the angular momentum in the z direction, right? And those are going to be plus h bar, they're going to be 0, and they're going to be minus h bar. So what does that mean? So we'll look at that in a second. If we want to know the magnitude of the angular momentum, the total angular momentum of the system, we can figure that out as being the square root of L squared. And since we know what L squared is, right, so L squared, right, so we're looking for the observed value that relates to the operator that I'm underlining in red here, and that value ends up being over here. So what we recognize is that in this particular case, we've kind of writing this out already, 1 times 1 plus 1 times the square root of h bar squared. In other words, that's equal to square root of 2h bar squared. So this ends up being the expectation value of L. Okay, so it's the expectation value, the magnitude of the total angular momentum. As I said before, we also know these eigenvalues for the angular momentum in the z direction. So what we can also see, by the way, is that h bar is less than the square root of 2 times h bar. So we know the angular momentum in the z direction is always less than the total angular momentum, square root of 2 h bar. So what does that mean? This basically means, so since h bar is less than root 2 h bar in this particular case, this implies that L and so the magnitude of the angular momentum and the magnitude of the angular momentum in the z direction cannot point in the same direction. And here's what we're going to do. We're going to draw something here. I'm going to basically show here's my z-axis, and I've got my y-axis here, and I've got my x-axis in this direction. And what I'm going to show is that in fact we've got a cone, and in this cone, the height of this cone as I've drawn it is, this is h bar. We've also got the magnitude of this angular momentum, and that's square root 2 h bar. And so we've also got at the top here, that means, again, this is sort of Pythagorean theory, so the width of this cone is also going to be h bar in here. Let me write this, is the m equals plus 1 component of the angular momentum of the L equals 1 state. Now, why have I drawn it as a cone? So let me state we have a cone because the x and y components cannot be specified. And we'll also say the projection of the motion onto the xy plane is a circle of radius h bar centered on the origin. Okay. And so that was this h bar in here. The last part of this particular section that I want to go through for chapter 6 will answer the following question. So can we specify L sub x and L sub y? Well, it turns out that if we think back to our commutators and commuting operators, it turns out that in fact it's arbitrary which direction we pick, which angular momentum we pick for a molecule. The molecule doesn't care, the atom doesn't care. These are arbitrary x, y, and z coordinates in the Cartesian coordinate geometry. So it turns out that all of these commutators are 0. So these all commute. Right, so remember, what am I drawing here in these square brackets? I'm basically saying these are the commutators. And if these operators all commute, then the commutator is 0. I won't show you here, but in fact this is problem 6.41 in the textbook, but we can show, and this is probably best done with Cartesian coordinates, but you can show that the commutators, I guess these are all the same, right? Lx and Ly, you're going to see a pattern. There is a commutator for all of these operators. Same pattern. It's always I h bar times the other angular momentum operator. And the point here is that these operators do not commute among themselves. So this all says that while it is possible to observe precise values of L squared and L sub z simultaneously, it is not possible to observe precise values of L sub x and L sub y simultaneously because they don't commute with each other, right? In other words, if we know L sub z and we decide that this is the direction that we care about, remember the operator for L sub z was much easier mathematically to work with, but if we know L sub z, that would tell us that if we look at the last two commutators, this would remind us that it is not possible to simultaneously know either L sub x, I guess we don't need the hat here, or L sub y. Okay, so these are the observables, the angular momenta. Remember that's different from L sub z hat, which is the operator. What we can also say is, in fact, this is just, you can take this to the bank. We do know that L sub x and the expectation value for L sub x. Okay, so that's kind of this, right? So L sub x is equal to L sub y, which is equal to 0. Okay, shall I stand corrected? Let's keep this simple for now. These are the average values, the expectation values, and those are equal to 0. So they do have an average value. What does this also mean? Heisenberg uncertainty principle tells us when we specify L sub z exactly, we have complete uncertainty in the equatorial angle, right? In the angle phi that's associated with that, we've got this spinning round, right? And so that has an LZ value. So we have complete uncertainty in the angle phi associated with L sub z. And again, go back to thinking about the angular momentum grip rule to help you about that. Remember what's special about z. There's nothing special about z. We could know L squared and L sub x precisely, in which case L sub y and L sub z wouldn't have precise values. It's just we've chosen L sub z because, in fact, the math is a little easier. So it's customary to pick LZ in the spherical coordinates because it's simply mathematically easier. And the last point is we have an inability to distinguish between the three directions. They're all the same. They all commute, and it explains our 2L plus 1 fold degeneracy, and we will finish the section at that point.